New unit. Solids, liquids, and solutions. Yeah. Okay. Go Shaps. It's Friday. So the first part of this unit, today we're going to be looking at the most important topic that pops up everywhere on the AP exam, and that is intermolecular forces. Okay? Intermolecular forces are also known as van der Waals forces. I'm going to shorten intermolecular forces a lot with IMFs. So, intermolecular forces, unlike intramolecular forces, deal with the attraction that exists between molecules in intermolecular force. Intramolecular force would be what? Within the molecule. So that would be a bond. Well, we're looking at the attraction between molecules. Why do we care? Well, if we didn't have attraction between molecules, everything would be gases. Not a very fun world, because we'd be gases too. And we'd all be like diffusing everywhere and mixing up, and it wouldn't be, life would be a gas. That's funny. You should have beat me on that. So in order to determine what intermolecular force you're dealing with, the most important thing is to figure out whether a bond is polar or not a bond. Back up. Whether a molecule is polar or nonpolar. So how do you figure out if a molecule is polar or nonpolar? The first thing you need to do. Lewis dot structure. Now I'm going to keep beating you up with this kind of stuff. Lewis dot structures have to be drawn. If you don't draw your Lewis dot structure, you can't determine if it's polar or nonpolar. Okay? Now, the force that exists between polar molecules is called dipole-dipole forces. And simply put, say this is hydrogen chloride gas, for instance. Right here, that's what this is a picture of. We'll say that's H. And no, we're not going to. Let's just say we have HCl. Well, you guys have drawn dipole moments, right? So chlorine is more electronegative, so arrow toward the chloride, partial negative, partial positive. Where does the dipole-dipole force come from in polar molecules? Because polar molecules have one side that's going to be higher in electrons, it's going to be more electron rich. It's going to have a side that's partially negative. Well, this then will be attracted, like here, to the side of the other molecule that's partially positive. And it's through this electrostatic attraction that molecules will come closer together in solids, not so close in liquids, but it keeps everything from being a gas because there is that attraction. Okay? Are we good with the dipole-dipole, why it exists between polar molecules? Now, dipole-dipole forces exist in other molecules as well, but we have a different set where we say the forces are actually so strong, we say they're almost like bonds, and we're calling them hydrogen bonded. There's hydrogen bonding going on. Hydrogen bonding is just a type of dipole-dipole that exists strictly between hydrogen when it's bonded with nitrogen, oxygen, or fluorine. Where do they get the cutoff? Why between these molecules? I don't know why they established the cutoff where they did. There's such a strong polarity difference in molecules that have a polarization in molecules that have hydrogen bonded to one of these things, that the dipole-dipole is super, super duper strong. So this right here is a strong dipole-dipole. And this dipole-dipole is called hydrogen bonding forces. Now here's the problem, and I'm kind of angry and bitter about this, like it keeps me up at night angry. I'm angry at the person who called it hydrogen bonding because what do you think students do? They call it a bond. This is not a bond, guys. This is an intermolecular force that's based on an electrostatic attraction. Okay? That is not a bond. So a big misconception on the AP exam is leading to this hydrogen bonding issue. About 2 years ago, there was a question that said, true or false? When water boils, bonds are broken. True or false? False. Very good. That means all of you would get this right on the AP. Yay. Why is that? Bonds aren't broken. What happens instead? Intermolecular forces are overcome. Okay, so I want you to jot that down. Anytime you have a change in phase from a solid to a liquid to a gas, intermolecular forces are overcome. Phase change, IMFs are overcome. We are not breaking bonds. I don't care that it says a hydrogen bond. It's not a bond. It's an intermolecular force. Okay? Got it? So hydrogen bonding as an intermolecular force is stronger than the typical dipole-dipole. Okay? It is its own category because of the strength, but in terms of how it works, it's still based on the same concept of a negative side of a molecule being attracted to the positive side of another molecule, based on the molecular polarity. Okay? So you've got to, again, draw out your Lewis dot structure, figure out if it's polar or nonpolar using VSEPR, and then put it in its category. So we've talked about things that are polar. What's left? Things that are nonpolar. So let's go to the next slide. Things that are nonpolar. Why are things that are nonpolar attracted to each other? Look up at the periodic table. Do you see how iodine is black? Okay, that means it's a solid at room temperature. Why would iodine molecules, I2, be attracted enough to other molecules to be solid? Any ideas? I'm going to pause here. So why does I2 have, or any nonpolar, have London dispersion forces? For one of two reasons. Something called an instantaneous dipole, where all the electrons, because we know all nonpolar molecules have electrons, where all the electrons might happen to end up more concentrated on one side of a molecular structure than another. At that brief moment in time, it has an instantaneous dipole. Doesn't last very long, but in that brief moment, it's going to be attracted to, like the positive side will be more, the partially positive side will be attracted to the partially negative side of some other one undergoing instantaneous dipole. Again, super weak forces. Don't last for very long. Have any of you ever seen an unbalanced washing machine? And it goes, that's kind of what I think of. When I start my wash, I think of electrons, yeah, and I think of chihuahuas. You'll learn about my electron and chihuahua thing later. But I think about putting electrons in the washing machine, and if it's unbalanced, that's your instantaneous dipole. That's what happens, kind of. Not literally, and it doesn't last that long, and you don't have to go into the electron washing machine and put them back like you do the clothes. It's just a metaphor, if that's even the word for it. Anyway, that's what I think of when I think of the unbalanced electrons. Now, there's another thing called an induced dipole, where when molecules slam into each other, you know how the electrons kind of, they could all shift to one side, okay? That also creates the same kind of polarity. Very brief moment of time. They're still nonpolar molecules, but the electrons kind of shift around. So let me ask you, how would you compare molecules with a few electrons compared to molecules with a bunch of electrons? Tell me about that strength of force. What do you think? Any ideas? I want you to be loud, and I'll probably make you talk in the mic after I determine if it's right or wrong. What do you think? If I have something with a bunch of electrons compared to something with a little electrons, what can you tell me about the London dispersion? I know you want to say something, Seth.
It's going to be greater because there's going to be more electrons to switch around.
Correct. Seth said it's going to be greater because there's going to be more electrons to swish around. And I use squishiness, actually, and I'm kind of shocked you used my word. Are you in my head?
I said swish.
Oh, you said swish. Oh, okay. And I did say swish, yeah, but I say squish. I say the electron cloud becomes more squishy, okay? So this is an important point. More electrons. Here's the word you need to know. The electron cloud is more, you ready for the magic word? The AP magic word, polarizable. It's the ability of the electron cloud to become polar. around that molecule, okay? The more electrons, the more polarizable, the more squishy. So if you draw out your Lewis dot structure and it's nonpolar, the force that exists between is called London dispersion. Okay, now I'm going to throw something at you and see if you can figure this out. Looking at the periodic table, I'm going to go down. I'm going to start with chlorine, and I'm going to drop to bromine. I'm going to drop to iodine. Look at the states of matter there. Chlorine is what state of matter at 25 degrees Celsius? What's bromine? And iodine? Solid. Huh. Why is that happening? More electrons. The electron cloud is more polarizable, so it has a stronger IMF. Iodine, having the most electrons, is going to have the most polarizable cloud, leading to the strongest intermolecular force. Does it make sense that things are solid have the strongest intermolecular force? They like each other the best? Yeah, it does. Okay? So the more electrons, the more polarizable, the stronger the intermolecular force. And I want you to add that. The stronger the intermolecular force. So some nonpolar molecules are going to have stronger London dispersion forces than others based on their number of electrons. Please don't say because the molecule's bigger. You won't get credit for that. I graded a question a few years ago where students said that and they got no credit. They had to say it had more electrons. Got it? Okay. Okay, and finally, one last thing. London dispersion forces actually exist in everything. Polar molecules, nonpolar molecules, everything. Why is that? Because everything has electrons and everything bumps into each other. And sometimes electrons, even in polar molecules, will end up more on one side than the other often. Okay? So just know that when you're asked to report London dispersion forces, they do exist in other things as well. But in things that are polar, London dispersion aren't the primary force. Okay? You really only have to report the primary force. You don't need to report London all the time. But I don't want to lie to you and just say, oh, that's water, it is hydrogen bonding, and that's it. No, there's some London in there as well, but it's not what's really causing it to have such a high intermolecular strength. Okay? All right, let's do an example now. Let's move on to the next little bit. To indicate the various types of intermolecular attractive forces that may operate in each of the following. All right, what family is this first molecule from? It's an alcohol. So we're going to draw it. Always draw it. Now, what I want you to do, because we haven't talked a ton about organic structures, pretend that that C is your central atom. Okay? That being the central atom, what can you tell me about the polarity of this molecule? Polar or nonpolar? Are you saying nonpolar because there's 4 areas? Because I might have to beat you. Why is it polar, though? There's 4 areas. Because there's something different attached to the center atom. 4 areas is only nonpolar when everything attached to the central atom is the same, right? The second you put different things on there, it becomes polar. Christmas colors, because I'm ready. All right. I shouldn't say that. Sorry. Holiday colors. All right. So if that's polar, what 2 possible intermolecular forces could this be then between these methanol molecules? Which ones could we have? Well, London's all the time. I'm not talking about that. Hydrogen bonding, dipole-dipole, or when things are polar, that's going to be one of the 2 primary things. Do we have hydrogen bonding in this one? Yes, because we have an NH attached to an N-NOF, is what I say, NOF, N-O or F. So this would be, I'm going to do HB for hydrogen bonding, DD for dipole-dipole, and LD for London dispersion. Now, there is some London dispersion in there, but it's not the primary one, so I'm not going to require that you report that. Okay, what about xenon? And here they have xenon as a liquid. So xenon as a liquid, What that means is xenon has to be attracted to some other xenons in order to be a liquid. So what could that be? It's just one atom. London. It has to be London. Xenons slam into other xenons. It could be polarizable. Because it's a, look how big. Xenon's pretty big, right? It's polarizable. So this would be London dispersion forces. Okay, what about C? What do I have to do? H2S. Draw it. Thank you. When you draw it, you will find it looks just like water, and sulfur has 2 lone pairs on it. Polar or nonpolar? Polar. So this is polar. So what intermolecular force do we have primarily? Dipole. Why isn't this hydrogen bonding? There's a hydrogen there. It's not NOF, not nitrogen, oxygen, or fluorine. DD, dipole-dipole. Okay, what about D? That's pretty easy to recognize as polar or nonpolar. It's just Cl attached to F. What does that have to be? Polar. And what is it? What's the force? May the force be with you. Polar, it is dipole-dipole. DD. And the last one's kind of a trick. Watch it. It's a trick. It's a trap. Intermolecular. Molecule. Molecule usually means covalent. What is E? Say it, Julian. E is ionic. If it's ionic, there is no intermolecular force because it isn't a molecule. They can't have intermolecular forces. Since it's ionic, what's holding it together? What's holding the crystal together? Yes, lattice energy. Muy bueno. Got it? So that's how you identify intermolecular forces. Practice, practice, practice that. Okay, now to do number 2, we really need to complete the table on the next slide. So here you have a list of stuff. This is the table in words. I'm not going to read this to you. This would be a good thing to read before your test. Okay, let's just jump to the table, and we're actually going to start filling this in. This is a table of pretty much, it's just solids. Every solid on the planet is going to fall into one of these categories. Let's start with the one you're most familiar with, our ionic salts, our ionic solids. Give me a few examples of those. That is so creative. What else? Yeah, we already, first period, third period, they were like KCl, NaCl, LiCl, and then they branched out into this to the +2 CaCl2. I'm like, let's try something with a polyatomic. Let's get really excited. Thank you. CaNO3. That's way out of the box. What'd you say? CS3. Wow. Ashley went way. Ammonium chloride. I'm good with that because that doesn't have any metals in it. All right. So those are all examples of salts. The type of bonding or intermolecular attraction that exists, we know is, we just said it, lattice energy, right? Which depends on what? Radius and charge. Okay. So that's good. Now, what are my typical properties? Tell me what you know about salts. What are some properties? Yes, high melting point, super high. If you don't believe me, over the holidays, when your parents have the roaring fire, go try. You've been trying for years? No luck, huh? All right. High melting point. Try to melt salt. Okay? It's not going to happen. All right? What can you tell me about salt solutions? Salt solutions conduct electricity. The solutions conduct, no, they have to be in solution, though, or 100% melted to conduct electricity. What can you tell me about when you touch them, how do they feel? Hard. Hardness is a characteristic, so yeah, that's good. Okay, so we all are very familiar with ionic solids. Now, what about other solids that don't have metals in them, that aren't ionic? And I'm not talking about lone atoms, things that are elements by themselves right now. I'm talking about all the other combinations of things. Give me an example. Things that are solid. Will you freak out if I write this? Because don't you know that that has a solid version? Okay. What other things are solid that don't have metals in them? Think biology. What now? Yeah, dry ice, CO2, it definitely can be a solid. What else? Proteins, sure. Carbohydrates, so what was our empirical formula, remember, for carbohydrates? CH2O, so I was actually going to pull in C6H12O6 and go, well, what about that? So any carbohydrate is good. Okay. All our proteins, all our organic stuff, all our biochemical stuff that doesn't have metals in it, all that stuff can be solid and obviously have to have some sort of intermolecular force or intermolecular attraction. So this is going to vary, guys, this intermolecular attraction. If the substances are polar, what are the possible intermolecular attractions? Dipole-dipole or? Great. And if they're nonpolar? Good. And that's going to depend because, look, we know that CO2, for instance, is nonpolar. I'm just going to draw a little. CO2 is nonpolar, okay? And notice everything we've written down at room temperature, CO2 is the only one that's a gas, right? Everything else we've written down, all your carbohydrates, those are polar molecules. And so those are either liquid or solid normally at room temperature, okay? Because the polar molecules have stronger intermolecular forces than the nonpolar ones. This is going to vary as well. I can generally say generally lower melting points in comparison to, you know, our ionics. Try to melt sugar too. Really make your parents happy. Yeah, you've done that too? Okay. So that takes care of compounds. So these are basically all our compounds, right? Now, what about when we just have lone atoms all by themselves? Someone pick an atom off the table. Sulfur. I heard sulfur first. Hold on. Hold that thought. I heard sulfur first. I like sulfur. I like phosphorus. Huh? No, tungsten's different. How is tungsten different than sulfur or phosphorus? It's a metal. Huh. Metal. Huh. Tungsten, copper, iron, all of those, right? Now I've got two specialty items that need to go in here. Carbon, and silicon. Those are the only ones you're going to be required to know that make network solids. Let's talk about those first. Carbon and silicon specifically have the capability. Carbon, it's due to something called catenation. It's willingness or desire for 4 bonds. And silicon is often used in things like quartz and glass, in the computer industry a lot. Those make 3-dimensional covalent networks. So it kind of looks like a lattice, but they're covalent. It's sharing. Unlike here in ionic, where it's a lattice truly attracted pluses and minuses to each other, here this is a covalent network. So it's 3D covalent bonding. This rivals the strength of your ionic bonds. You've heard about diamonds being as hard as they are, right? Okay. You've heard about silicon, glass. You know the high melting points of that stuff. So these things have super high melting points. So for your information, anything with silicon like SiO2 and it will be, we're gonna term it as a covalent network. It's going to be super, and it falls on that metal, non-metal borderline, so that plays a part why it's capable of sharing so much stuff. So any questions about the covalent network? All right. Metallic stuff. The type of bonding, what goes on with metallic stuff? What can you tell me about metals, some properties of metals? They what? And by the way, let me go ahead and we'll talk. You're close, Julian. These are hard as well. Super, super hard. Diamond is used to cut stuff. Okay. All right. Now go back here. Metallic stuff, it's going to vary. Hardness varies. Have you ever seen gold, like 14 karat gold? Super soft. Okay, I don't know if you've ever touched it. But what else is specific about metals? Why wouldn't we want metal in a metal rod in the pool when it's thunder and lightning? They're conductive, and that's the reason I wanted you to recognize that is because that has to do with the bonding type. People always say, oh, metals have a sea of electrons, meaning, say we have, and I'll just draw a little picture, copper. The way they bond is not, when we have metals, they're actually kind of bonded through delocalization of electrons. So electrons don't stay in bonds when metals are all around each other. The electrons kind of jump around, back and forth, and they're just all sharing everybody's electrons. It's one big commune of electrons. And so, in a sense, it's kind of like a bonding. That goes here. The term we use for that is delocalized electrons. That's why metals have the capability, being ductile, they have the capability of conducting electricity. It's because of the ability of those electrons to move like that, okay? All right. And again, all of these are going to vary from metal to metal because metals are so different. When I'm done with lecture, if you all remind me, I'll take out some iron and then take out some tin and just show you the difference between iron and tin holding in your hands. It's very, very different. Okay. So that takes care of all the metals. That takes care of carbon and silicon and any others that do covalent networks. What about all the nonmetals? What makes sulfur? Have you seen sulfur solid? It's white powder. Okay. Phosphorus, white, red, depending upon whether it's like P4 or because we get different combinations of phosphorus, but we still consider it to be lone atom. What keeps those as solids then? What force does it have to be? London dispersion, exactly. All London dispersion. There's no polarity in a lone atom, so it has to be London dispersion. These are typically soft. Man, they stink. When anything stinks, it means it's got a small intermolecular force because it's easily going off into gas phase, right? Going off into gas phase is how we smell it. So I'm going to write stinky. Okay, and that's because of the low intermolecular forces, the small intermolecular forces. Okay, so now let's just go ahead and go back to the previous problem. For each of the following pairs of substances, predict which will have the higher, well, it's pretty much done for you. Tell me why. So let's just identify the actual intermolecular force. CuBr2, what is that? Why is that harder to melt than Br2? This is ionic, so it's lattice energy, right? Versus Br2. Good. London dispersion. Why is Cr2 easier to melt than SiO2? What is SiO2? It's a covalent network. And then what about CO2? I can draw it for you if you don't remember. It's not dipole-dipole. Sorry, Charlie. That's nonpolar, right? So it's nonpolar is London dispersion. Chromium versus little bitty sulfur. Sulfur seems to melt a lot easier than chromium. What is sulfur? London dispersion because it's a lone atom, right? Versus chromium, what type of bonding does it have? Metallic. Good. Metallica. Just kidding. Ooh, tricky. Why is CSBr easier to melt than CAF2? Bond? Bond? Just kidding, not bond. What? Yes. So I'm just going to say, I'm going to point to this one and say lattice energy larger. Why? Small radius, smaller radius, and higher charge. Wow, so y'all learned something last unit. That's awesome. Okay, jump to number 3 and we'll be done in less than 2 minutes if you guys are on it. Ready to be on it? Okay, O2. We're going to tell me, just basically you're telling me where on the chart it belongs. This one I can go 2 ways. I understand why you might say lone, but it's really 2 together, so I'm going to go with molecular. And I'm going to take this a step further. What intermolecular force would be holding this puppy together if it were solid? London dispersion. Good. H2S, I've already drawn it today. It has 2 lone pairs in the center atom. First, find it on the chart. Where does it belong? Is it ionic? It's a compound, right? So it's either ionic or molecular. Molecular. What's the intermolecular force? Dipole-dipole, because it's polar and it's not hydrogen bonding because there's hydrogen's not attached to NOF. Ag. Ag. Metallic. And we say delocalized electrons. KCl. Isn't it ionic? All right. Don't you think? It's like rain on your way. All right. Y'all better laugh really loud so people can hear that. Thanks. So that I'm not like talking to myself and singing to myself. Ionic, and this would be lattice energy. Si. Covalent network. Oh, don't die now, smart board. It was my singing. It needs a little break. So let's go to the next one. Aluminum sulfate. Ionic, yes. It's still dead. Man, I broke it with my voice. There it goes. It just reconnected. So this is covalent network. This is ionic. So this is 3-dimensional covalent bonding all around. So one bonds to another, which bonds to another, which bonds to another. That's what I mean by network. This is ionic, lattice energy. Neon. A molecular, really? I heard one person say it right. It goes in the molecular column. It's a lone atom, right? And what's its intermolecular force if it were solid? London dispersion. Silicon dioxide, again, covalent network. Oh, looky, what's this one? NH3. It's got a lone pair on the end when you draw it out. First off, where does it fall on the table? It's a compound, so it's molecular. And what's its intermolecular force? I didn't trick you guys. Good job. Magnesium oxide. Man, there's a lot of these. And this one are the same. The compound, ionic, lattice energy. And the last one is methane. No. Covalent network is just for carbon by itself. Okay, we know methane is a gas, right? So how could it be a covalent network? Those are supposed to be strong and hard solids, okay? It's not that. So carbon alone is the only time you're going to make that network. What? Molecular and polar, nonpolar. Nonpolar, so it's London dispersion. Good job. That is all for today.